Okay, let's go ahead and get started. Hi, everybody. All right, today we're doing pointers. Pointers are awesome. Let's just get started. Any questions from the videos? No? Nothing? You all watch the videos? Okay, I made a mistake, a slight mistake. And the mistake is that I didn't, like this last time I gave you videos that I should have given you some of the time before that, and I realized that later because like people were confused about what new was, and I didn't realize I gave you the wrong set of videos, which means we're also a little behind, so some of the stuff I'll talk about today will unfortunately be repeated on the videos you'll watch for next week. Does that make sense? So it's my error, but you'll get information more than once. But to jump in, we're going to go ahead and do a problem thing, because it's fun, and then we'll talk about it. Hi, how are you doing? So I'll hand these out, step through this with, friends, partners, anyone you want to. We'll talk it over in a few minutes. You're welcome. Did y'all get some over here? Y'all did? 1, 2. Some more. Here, just pass those over and around and back. Hi, I'm going to pass those down that way. And what? Oh, you get one of these, sorry. You should have something that says dangling pointers and memory leaks. Does anyone have one that says node operations by accident? Okay. Pass the extras back up this way, please. Sorry about that. The printer got jammed. You're looking at the wrong one because I gave you the wrong one. No, you didn't miss anything. What happened was as I was grabbing these off the printer jammed and like it put all of them together when it shouldn't have. So just pass it to her right there and she'll pass them across. That's what I want you to have, yes. But you no longer have anything and you just handed me this. Why don't I give it back to you and you can take some? You're welcome, Zeta. All right, who doesn't have one of these dangling pointers? All right, I'm just going to hand that to you on your way back. No, he just did it that way. I mean, you can do it either way you want. Any of those extras right there? Zoe has some. My computer has disappeared on us. Thank you. One of these. Oh, sorry about that. Yes, sir. I meant it exactly like it's there. I'm going to go home with my family and cook a turkey and a whole bunch of pie. Why? Like, really? Why? What are you doing? Uh-huh. Well, uh-huh. I don't. I just like rugby shirts. I know. I know. I know. I get that a lot in the winter. I have some sweaters too that I wear, except they're all like dirty, and I haven't taken them to the cleaners, and so I have rugby shirts. So I don't know. I just like them. Just do. They're like the simplest, easy, most rugged, reliable shirt, and I just have like a big stack of them in my closet, and I take whatever one is off the top, which is why I end up wearing black ones because I wear them once and they end up on the top, and I have to make like an effort to get a different one out of them. All right, obviously, since I'm being asked weird personal questions, we can start going over this. So, who thinks they know the answer for what's going to print out here? Anybody? I've got candy. Tell you what, triple candy if you're actually right. How's that? It's a trick question. Yes, let's go ahead. Okay, well, let's step through it and see what we say. Where do we start? Uh-huh. We started. And how do we know that this is a pointer declaration? A type, a star, and a variable name. Yep. Yes, so what happens is new creates a box somewhere, and it puts 10 in it, and it returns the address of that box, and we store it in X. So now we have a box that has the address, and the address is of another box that holds the value 10. Okay, keep going. And what is that going to be? Yeah, we don't know. The computer's going to give us something random. When we run it, we'll see that. And then this. And we're going to follow. This means follow the pointer when you get there. Print it out. So it prints out 10. Okay. Yes, so what delete does is delete says, we have this box that's holding something and we're not going to use it anymore. So you don't have to keep track of it. Okay. And what does this do? Yep. Has X changed as a result of this? No, it hasn't, right? We haven't done anything with X. We've just said delete means follow this pointer, and when you get to the box at the end, we're not keeping track of that anymore. So it's deleted. So, and this will still print out? What will this print out? Okay, let's keep going. So we don't know what this is going to print out yet, right? This is like totally the trap trick question. Okay, so I feel, do you have a question? It will. This one will print out the address of where 10 was, because X hasn't changed. But when we dereference X, when we say star X, and we go to that address, what's going to be there now that it's deleted? We don't know. Yeah. It follows that address, and when it gets there, it does some operation on that box that's deleting it. Because the original box is just holding an address, and delete is not operating on that box, it's operating on the address that's stored in that box. So delete takes a pointer, follows a pointer, when it gets there, it does the delete operation on the thing that's there. Yes, that's just the way the delete command works. Yes, but not the address that 10 was stored in. Yeah. All right. Now we declare this thing y. What is y doing? What is y now? What? A pointer, yeah. And then what does this loop do? Uh-huh. Yeah. How many does it create? Oh, sorry, I'll put 100 in there. Sorry, I meant to put the code over on my laptop before I left my office, and I forgot, so I just typed it up again. Uh-huh. Yep. Uh-huh. So when this is done, it's pointing at one box. And how many boxes did it make? Yes, 99 of them. It created 100 of them, but 99 of them, we no longer know where they are because we no longer have their address, right? So what is that called? A memory leak. When you use new to create something that you lose track of and you can't get it back later, that's a memory leak. How many of y'all think memory leaks are good? How many of y'all think they're bad? Memory leaks are really bad. I don't know if this is in the video, but remember we were talking last week about linked lists and the stuff that they were used for. We'll talk more about that today. One of the things linked lists are used for are for keeping track of like what programs are running. So the operating system keeps a linked list of all the running programs. Windows 95, how many were born in 1995? Anybody? Thank God. In a few more years, I'm not going to be able to get that. Windows 95 came out, and it turned out that if you opened and closed programs over and over again, your computer would crash. And the reason it would crash is because it set aside a certain amount of memory to keep track of programs, and it stored them on a linked list, and it had a memory leak. And when you open and close the program, the information kind of stayed there, and they never reclaimed it. So if you open and close programs, Windows would just crash because it ran out of space. Yeah, so memory leaks are bad, okay? Memory leaks are very bad. So when we're using new, we always want to try and pair it with delete. All right, so we create 100 things, we have a memory leak, and then we print out X again, and we try to print out X again. What does this print out? Same memory address. And what does this print out? Anybody want to guess? Okay. So how many of y'all, let's go, so here, what is this X going to print out? The first time it prints out, what's it going to print out? 10. Everybody agree that that's going to be 10? Anybody think it's going to be something else? The second time it prints out X, what's it going to be? It could be a compiler error. How many of y'all think compiler error? How many of y'all think segmentation fault or some sort of runtime error? How many of y'all think there's going to be a value in here? What value do you think it's going to be? 0? Okay. How about down here? What is this one going to print out? Same as the first one? How many of y'all think it'll be the same? All right, let's run it and see. I'm totally messing with you. There's absolutely no doubt about it because there's no way you would know this not having seen it before. And I'm pretty sure I know what's going to happen because I ran it like 100 times today, the morning, to see what would happen. Okay, so it compiled cleanly. So I'm going to run this, and here's what we expect to see. We expect to see a memory address print out and a value that we said was 10. We expect to see a memory address print out and a value that we didn't quite know what to expect because it had been deleted. And then we see a memory address print out and another value, okay? Now, I think the values are going to be 10, 10, and 4. And thank goodness I was right, okay? So, all right. So, go ahead, and here's what we see. We see the same memory address 3 times, right? 7 FECA 4000 E0. Sounds like something from like episode 1 of Star Wars. So we see the same memory address print out so that once X is set, it is not being changed. It's the same memory address. But the value that's in it is changing each time. All right? Now, let's go back and look at the code for a second, and we can talk about why. So here's what happens. X becomes a new int with a value of 10, right? So we create a box, we put the value of 10 in it, everything's good, we're happy. Then what happens is we output it, and then we dereference the pointer, and we follow that, we output it, we see the address, And then we dereference, which means we go to follow that address to the box and we print the value in there, and that's 10. Now we delete x. Here's what delete does. Delete just marks that box available for use later. It does not change any of the values in the box. It does not zero out the box. All it does is tell the compiler, hey, we're done with this box. If you want to use it later, you can just go ahead and grab it. So now, what we do is we print out x again, and we see that it's the same address. And then we dereference x, and you know what happens? Since it's the same address, it goes right to that address, and it looks in what's in that box. And what's in that box? 10, because it has not been reused yet. That memory address has not been reused yet. All right, now we create something called y. Yes? Okay, I'll talk about that. Let's just talk about it now, since yes. So her question was, how many times can we reuse the value in the box? Once you have deleted it, and if you reuse it again, that is bad. And not just a little bad, it is horribly bad. This is what's called a use after free error. And using it after it's been freed. Free is another word for delete. Free is like the C++, the C version of it. So it's a use after free error. We have deleted this, and we're still trying to use the value. When you do that, your program will behave unpredictably. And even worse is that if you are writing an important piece of software, there are bad people in the world. Everybody agree there's bad people in the world? People range from imperfect to suck. The sucky people can use this to take control of your program and make it do whatever they want. This is a huge security violation for programs. Now, I'd be happy to explain that to you why, but you have to come take my information assurance class after you've had a bunch of other stuff, because it deals with how the computer lays out memory and what happens. And so it gets a little complicated, but this is actually a security problem where people use something after it's been deleted. All right, then what we do is we say, okay, we declare y, and y creates 100 new things. Now, what is the compiler and the computer going to do when it creates a new one? It's going to say, oh, I'm going to find one that is available for use, and guess what? We deleted it before, so now it is available for use again. And so I would just go ahead and grab the exact same box I used before, and this time I'll put 4 in it. Now, when I originally did this, I did it like 1,000,000 times because I wasn't sure where the computer was going to put things. It actually turns out that you don't even need the loop. On the Mac, the compiler will reuse the same box immediately. But I also wanted to have a demonstration of a memory leak, and if I only did it once, I didn't have a memory leak, right? So it turns out that the very first box that this one uses, when it goes 4, is the exact same one it used for X before. Because when it deleted it, it said, hey, I'm done with this. You can use it later if you need it. And the very first time we declare something with Y, it goes, oh, I need a box. I'll just use the same one I used for X before. Yes? Uh-huh. No, you cannot assume it'll always be 10. And that's exactly what I'm trying to show you by doing it again down here after we've done some other memory things. Because did you remember this one turned into 4? Uh-huh. No, it did delete it. But the delete operation does not erase anything. Exactly, that's exactly what happened. That doesn't mean we can reuse it safely. There's a difference, right? It's kind of like, let me think of a really bad analogy for this. Uh-huh. You can guess that most of the time it's going to show the same number as 12. Yes. Uh-huh. But do we ever want to be in a position where we're guessing about things? I'm not going to put this on an exam because it would be unfair for you to guess what's going on behind the scenes, right? But I want to make clear to you that after you've deleted something, you don't ever want to use it again. Okay? Because that's, what is that? Bad. It's a security problem. Literally, I mean, let me just talk about security for a second because you'll hear about this. In a program that takes input from the user, an evil user can actually put input into your program that is binary code that the computer can understand. And if they format this input correctly, what will happen is they'll take advantage of some software error that you made, and their binary code will get loaded into the computer and will start running. So your program here is like, printing out some stuff. If you have input, they can write something that will make your computer erase the hard drive or send viruses to all your friends or something like that. And most of the stuff you hear about in the world about attacks and worms take advantage of software flaws to do this. Okay, does that make sense? So it's crazy. The first time I saw this, I was in graduate school and I read a paper that showed how to take over things, and I was just, it changed my life. I don't know for the better or worse, but I looked at that and I was like, oh my God, it never occurred to me you could possibly do that. So I want you just to be aware that if you screw up, you're probably going to, destroy civilization. But no pressure, right? No pressure. But anyway, this is a use after free error, and that's a problem because if you continue using after it's deleted, it might work for a little while, but then it might turn into something that you don't expect. Yeah? This is also a use after free error, and the difference is that this time we purposely forced it to be a different value so you could see that the value changed. That makes sense? Sir? Nope. Yes, but you don't have any control over when that box gets used. Right? Here, this is a small enough program that because we delete it and call it right away, things haven't been changed. But in the larger program, you cannot guarantee that. So, star X? Yep. Because what we did is over here, in this loop that looks like it does nothing, we have actually created a whole bunch of boxes that have the value 4 in it. And what happened is because we deleted this box up here, when we created a new one, the compiler goes, oh, I have an empty box. I will just stick a 4 in here. And then there's 99 other boxes. I mean, I can show you really fast if you want, and I think it'll work. I mean, this is not something that you can always count on, but I think just making one box with 4 is enough to overwrite the same thing. And that's exactly what it did. I made only one box with 4, and because of the way my particular computer is working, it reused the same box it was using for 10 immediately. The goal of this is not to give you a rule of when it's okay to reuse pointers, because it is never okay to reuse pointers. Never, ever. Right? I'm just showing you that in this particular case, on this computer, it happens to do that. But there's no guarantee that this is how it will always work. The point of this is to show you bad things happen when you reference pointers that have already been deleted. Okay? That's bad. Yes? Uh-huh. Nope. You don't have to redeclare it because we've already declared that there's a box you can have to hold an address. It's just now we're putting a different address in it. Yep. And so I'm going to run this, and what you're going to see is that, here it's the old address and it's printing out 4, and then after we do this new, it's going to print out whatever new address that has a 5 in it. So So this is the old address, right? 134.0.0.0.E0, and now it's 134.0.3.A.10. And so this is probably if we were able to work out the math of how big the boxes were and how many we built, this is probably like, 101 boxes of the size of int down, if you're counting in hexadecimal. Yep. 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 Yes. Yes. So let me make one other thing. The problem with this use after free error is that here we have a dangling pointer. And a dangling pointer is a pointer that points somewhere that you don't know, right? You have done something to the thing it points at, and you haven't changed the address. And dangling pointers cause problems. They cause bad problems. All right, so this makes sense? Everybody kind of see where we're going here? The point of this is when you delete something, it's best to just reset the pointer to null, depending on what you're doing, right? That's safe. Now, let me just show you one other thing. I'm going to show you one more thing that happens with pointers so that you know. Say we say x equals null. We have just set x as a pointer to point at a safe place, right? Because we know that null is essentially 0. We're pointing at address 0, and we know that we're never going to actually store anything there. We've just saved this null as a safe place to put things. What happens now if we try to print out what's dereferenced at x? Anybody know? We're going to print out a 0. It does have an address. It's actually 0. Null is a synonym for 0. It's just easier to think of as null. So here's what I did: is we added this code that prints out, makes x 5 and prints it out. Then I make x null and I try to print it out. And when I run it, what's going to happen? Segmentation fault. Segmentation fault. So what happens is if you have a dangling pointer or a null pointer, well, let me separate these two. If you have a null pointer and you attempt to dereference it, you will get a segmentation fault, right? So if your program's running along and you get a segmentation fault, you've either tried to dereference a null pointer and that made it crash. Or the second thing that can happen is if you have a dangling pointer, sometimes the dangling pointers will be pointing in memory someplace that makes it crash as well. Does that make sense? So the example I showed you of our dangling pointer with the use after free error, there was actually something there that we could use, and it printed out right. But sometimes if you have a dangling pointer, you will also get a segmentation fault. So the difficulty with working with pointers is that your program crashes all the time if your pointer operations are bad. And it gets a little annoying. Yes, sir? Why is 5 there? Because we created a new value of 5 and printed it out before I did the dereference. I'll show you back in the code. So we had a question of whether we could reuse x. So I reused x to create a new box. Then I set x equal to null and tried to access it. Yeah, it's fine. This is exactly what we use for. We created a new thing that has a value of 5 and set x to that. No problem. No problem at all. It's okay to use the same box. It's like, can we have something that's an int and change it to another int? Absolutely. No problem. Yes? Uh-huh. Yes. If we did something here where we did delete y, what we're doing is creating something and then deleting it. But, and I'm not sure about this, I think what would happen is we would still see this become a 4 because it would be pointing at a different place. But we wouldn't have a memory leak. The thing about this is it's hard to see the memory leak. I can't show you the memory leak. Something bad is happening with my computer. I don't know what. Maybe we've memory leaked it to death or something. So we shouldn't have. Whoa. Stop. Okay. Okay, so here what I've done is I've actually deleting everything that we're creating, but I have a feeling, and again, I'm not sure on this because there's no guarantee that if we run it, yeah, we're still getting a 4 there. So even though we've used it and deleted it. So. Yes? It's when you have a new and you no longer are recording the address or have any way to reach that address because you don't have the address of it stored anywhere anymore that you can reach. A dangling pointer is a pointer that points in an address, but that is an address that we're no longer sure what the hell's going on there. So it's like either we're pointing at something we've deleted, or we're pointing at something that, pointing at something that deleted is most common, or you've done some weird pointer operation and you're pointing off into space. But most often it's pointing at something that's been deleted. Yes, X is a dangling pointer once it's pointing at something that has been deleted. Yep. Yes. Uh-huh. Yes. Exactly. It's like a reservation. Yeah, that's a good way. All right. Yeah. No. If you try to delete a null pointer, you will also get a crash. You want to see? Comment this out. What? No, I guess you won't get a crash. Anyway. So I'm just, here, what I'm trying to show you here are the mechanics of this, rather than give you rules of when you should or should not, because as you progress through your career in computer science, assuming you do the smart thing and leave physics, just messing with you, sorry. Then what'll happen is, like, you'll be using pointers for a lot of different things. And so there's no hard and fast rule I can tell you, because it depends on what you're doing. But in general, after you delete something, you want to make sure you're not using any pointer that points to it. That's the best rule that I can tell you. Yeah? Do we know what Y points to? Well, so before I put this delete thing in here, right here, before I put that in there, oops, what happened is we looped through this and we created, like, originally we had 100 of these, but I showed you that it worked with only one. So if we go back to what we had there, if I can type. If we go back to what we have here, what's going to happen is 100 times we're going to create something new and store that address in Y. So 99 times we're going to create something new and then immediately forget the address. So what's going to be stored in Y here is the address of the very last thing out of these 100 that was created. Oh, no, we have no idea what's there. Do you want to try and do stuff with it? In fact, I think if we print this out here, we're probably going to get 10. That's my guess. And again, the whole point of this is not to show you, yeah, then it's seg faults. So we got, wait, 10, 10 seg faults. I don't even know what's going on anymore. Oh, when we tried to print it out, it was pointing someplace random and it died. And if we can see what address was in there, but anyway, this isn't important. It's just kind of fun. So for me, so it was pointing at 0 for some reason. All right, how many of y'all are baffled by now? A little bit. Okay. So here's the general rule that I'm trying to show you. After you delete something, don't use the pointer to it anymore because it is a dangling pointer. That is our whole takeaway. If you make a whole bunch of stuff, you have to keep track of all the pointers to them or they are gone. And that is a memory leak. Those are the two things. All right. Those are really what I was trying to show you. And if you reuse a pointer after it's been deleted, weird stuff will happen. Is that good? Are you all happy with that? Can we simplify it, like reusing a pointer after it's been deleted makes it weird? And I just showed you a bunch of weirdness because I don't even know why I did that. It's probably a bad idea. Other questions? Yes? Yes, the second rule, what was the first rule? Yeah, a dangling pointer. The second rule is if you make a bunch of stuff, you have to keep pointers to them all or they are gone forever. So by my analogy, remember last time we were talking about going fishing and tying all the Coke bottles together in a string. If you cut the string, everything that is below that is gone. It's gone. You can't get it back. All right. Is that good? Let's move on to more useful stuff. But let's wiggle and take a break, stand up, stretch, do whatever you like to do for a moment. The null one. Yeah. That's kind of when you, null is a marker that we use so that when we check the value of a pointer, we know that it's not pointing at anything. So you have a box. So if you have something that's set to null, you have a box that can store an address, but what's actually stored in there is 0. Because 0, there's address in there that's 0, but 0 is a special address that we just use to mean that there's no current address stored in there. Yeah. Mm-hmm. Yes. That's exactly what you do. Oh, we tried to print it out. Yeah. No, we tried to dereference the pointer, and because it was null, it crashed. What we did is we said, go look at this box. It has an address of 0. Go to that address, and when you get there, print out the value. And so, but it was 0, so it crashed. Yeah. Oh, sorry. Oh, man. Look out. Man. I'm going to get one back there for you. The Butterfingers just aren't going very far today. Normally they're nice and heavy. All right, so let's get back to what we were kind of talking about last time and how we're going to use these pointers, okay? And as we talked about last time, it doesn't make any sense for us to always have a named thing. For example, X can be a pointer. I'm going to draw pointers like this with little lines to a box that has a value in it. This box has a name, it's X. This box has a value 10. It doesn't make any sense for us to do this because we haven't gotten rid of the problem where for each box that has a value, we have a name. And the way we're going to get around that is we're going to start working with classes and objects that contain within them a pointer to something of their own type. And these are called self-referential classes. And the idea is up here we will have some sort of data. And when I say some sort of data, it can be like one piece of data, it can be 100 pieces of data. It's data, right? For our examples, we're going to pretend it's just one integer because that is a simple for an example. But when we're working on the projects, this data might be everything that you need for the Reynolds subject. Does that make sense? And what we're going to do is we're going to have one named thing that points at the first one, and then we're going to have a daisy chain of all the others linked together in one long line. And then the last one, the pointer will be pointing at null, and in general, I will draw null like that, like a electronic grounding symbol. So as we build this, we have one thing that is of type a pointer to a node, and all these things over here will actually be of type node, but inside they will have a pointer to the node themselves. Do you remember the analogy, the Coke bottle analogy? You're out fishing, right? Here's everything that is a pointer is a piece of string, and everything that holds data is actually the bottle. So we have a piece of string tied to a bottle. This bottle has a piece of string tied to the next bottle, to the next bottle, to the next bottle, which has no string tied to it. Yes? Mm-hmm. Nope. It's going to be private data member as part of the node class. It is not. We're about to write the node class. I'm just calling each one of these things a node, and then we'll write it up and we'll do some operations with it. We could create a class called Reynolds Subject, and Reynolds Subject would have all the data that we needed for a Reynolds Subject, plus a pointer to another Reynolds Subject, which is exactly what I spent last night writing code that did, and I will post the assignment today. Okay, it does this. So what we're going to be doing is replacing our vector of Reynolds Subject with a linked list of Reynolds Subjects. And the idea behind this is twofold. First, you will get to experience how to operate with pointers. And second, actually, that's all you're going to get. You're just going to get to work with pointers. And this is the simplest example of pointers so that you can learn the mechanics of it, right? Learn the mechanics, because in other classes, we're going to do really amazingly cool stuff with this. But before we do cool stuff, we want to make sure that you're familiar with working with them. Does that make sense? So, yes?
So we're doing that for project 5, right?
Yep.
Do you know when
Yes. Oh, I didn't say that. I just said I know it'll be up. Yeah, it'll be up today. I've written the code. I just have to write the project description and post it. So I always write the code first to make sure. And I will be more explicit about error handling this time, since that caused confusion last time. Okay, so everybody see where we're going with this? Pretty much, kind of, sort of? And, you know, my computer keeps blanking, I think. Wake up, computer. There we go. Okay. All right, so here's what we're going to do. We are going to go ahead and write what we need for a node class, just as a simple example. All right. Who wants to help me with this? We're going to write a class. How do we start writing a class? What? How do you start writing a class? Class. Class. And we're just going to call it the node class. This is a simple example. And what do we always have at the end of a class definition? A semicolon. What are we going to have in here? Public and private. And what is the private portion of this going to be? We're going to have two pieces in the private portion. We're going to have some data and something else. So in the private portion, we'll have an integer, and we'll call this data, because our data for this example is only an integer. And then for the link to the next node, we have a pointer to another node, which we would just call next. Make sense so far? So what we're doing is we're creating an object. The objects are going to look just like this, where they have some data, and then they have a link to the next thing. And we're going to be able to hook them all together. Yeah? Say again. Yep. Yep. Nope. They have to be the same, because we're creating a class. A class is a blueprint that creates objects. What we're saying is that inside each one of these objects, there's going to be the address of another one of exactly these type of objects. So they're all homogeneous. The objects are homogeneous. In other applications, they may not be. You could have a node class that had links to strings and dogs and stuff like that, whatever you wanted. But this is simple. We're just building the thing that I tried to draw very elegantly using my massive art skills over there. All right, so if we have these two private things, what do we need for them? Yep, we need getters and setters. So that should be it for int, right? We're going to set an int. What do these things look like? What do these things look like for the getters and setters for the node? Is it going to be a node or a node star? Is it an actual node or is it a pointer to a node? Pardon? How many of y'all think it's a pointer? How many of y'all think it's an actual node? Pointers have it. So we can either get the next node or set the next node. And that takes a node pointer as an argument. Everybody with me so far? There's one other thing that we need here. What else do we need? A constructor. What does that look like? Yep. Great. So let's write some of this stuff. So the first thing we need belongs to the node class. It's the node constructor. It takes no parameters. What are we going to set inside here? What do you mean nothing? We don't have to do anything at all? Okay, so we should set some values, and we should set some default values. What default values should they be? Yep. Next equals no. So when we create these new things, it's actually important to make the value null. And the reason it's important to make the value null is that if you don't set this to null, what value is this going to have? You don't know. And what happens when you start following random pointers around? Bad things. Bad things. Okay? Bad things. So that's a constructor. I'll tell you what though, wouldn't it be nice if we were able to like have a constructor that set the value as well? What do you think? Do you want to write one that we can put a value in there and have the data set? How about this? I'm going to cheat and just use a default parameter. Like that. So, and then what I'll do is down here I'll say int I, and then I'll say data equals I. So, what I've done is instead of having one that just creates the initial value, one that creates things and doesn't allow setting the value, I said we can set the value, but I also set a default parameter to 0, so we don't have to write two separate constructors. Sir? Nope, it goes in the prototype. Yeah, it's a weird thing about C++. Oh yeah, sorry, I put it in get data, didn't I? Sorry about that. I thought I was being all clever, but I put it in the wrong spot. Here. Oh, good duck. All right. So that should be our constructor. And the other things are all pretty straightforward too, right? Belongs to node, it's set data. We get some integer I, and then we just say data equals I. When I do this, when I say data equals I, what data is this? Who knows? Nobody knows? It's a mystery? You answer questions all the time. I forgot to write my pick on people program again. Ugh. How about Dakota? I'll pick on you, because I haven't picked on you all semester. Where does this data come from? Yeah, in this thing, node set data int I, data equals I, what variable is this referring to? All right, that was mean. I'll give you a hint. Where do we see data in here? The private data section. Yes, just like everything else we've done. So, was that shocking? Okay, same thing for get data, node, int belongs to the node class, it's get data, and it doesn't take any parameters, and it just returns data. And then we do data set data. We need a node star, node class, get next node. And what does this return? Next. And then we need a void, belongs to the node class, and it's called sec next node, and it takes what as an argument? Yeah, keep going. Yeah, right. Return next. Yeah, I do. Okay. And we take some new node, and then we say next equals new node. Right. So let's give this a main really fast. And what I'm going to do is I'm going to compile it with an empty main just to make sure there's no errors in the class. That's what I thought was going to happen. Okay, so I have an error on line 8. Oh, needs it just clearer. There we go. That'll probably fix everything. Yep, there we go. All right, so we have our node class and we can do things with it. What do you want to do with it? How about we create a node? Okay, so let's do this. So what is this going to do? And we're going to draw pictures for this. How's that? If I can find the eraser. So we have one line of code here. What does this do? Yep. Uh-huh. And then what is this? This box has a pointer to it. What's this pointer pointing at? Points where? Like that? Nope. When we create this, when we create the object, the constructor gets called. And what does the constructor say to do? I will scroll back up to the constructor so we can see it all at once. So here's the constructor. So when we create a node with 100, this gets set to 100 because that's what the parameter is. And what happens to the pointer? What does that get set to? Null, and we draw it like this. So we have a box, and it's pointing. What is the name of this box? What's the name? The name is X. We named this box. Okay. Does that make sense? This is an artificial example to show you the mechanics. This isn't necessarily how we're going to do it always, but I just want to step through the mechanics first. We did not. We just built one box with a name that has a value. Do you want to do it the other way? So we just built one box this way. We're going to do it several different ways throughout different examples. So you're going to see this, I think, 2 or 3 times before next class. All right. So we built a box that has a name. Let's do something else. Let's say this. X. So here's what we want to do. The thing we want to do next is we want this value right here to be pointing at another box over here that has the value 200 in it. How do we do that? And I'll give you a hint. How do we do that without giving this other box a name? Yep. Okay. So here's what we're going to do. We have this thing X, and what we're going to do is we want to set the next node, oops, sorry, not to a value of 200, but to a new node that has a value of 200 in it. And let's break this down for 1 second, because in fact it's not quite right. We have to do something else here. It looks like this. here's what we're going to do to create another box. What we're going to do is we're going to do star X. Yes? That's what we're going to talk about. So here's what's going to happen when we're done. We have a box named X. It has a value and a pointer. When we're done with what we're about to do, this pointer is no longer going to be pointing at null. It's going to be pointing at this other box that has a value of 200. Okay? Another node. And this one has, so we're kind of linking these two things together. We're going to do it a bunch of different ways. Okay? Yes, it is. We named this is a node. A node contains two objects. It contains a piece of data and a pointer. So we created a node. We named it X, right? Oh, you're correct. My bad. Sorry about that. I totally doing the wrong thing, which is exactly what you wanted to be doing. So, okay, so X is a pointer to this thing. Thank you for correcting my error. You're absolutely right. Yes, sorry, X has the address. We could also do it, anyway, we could also do it a different way, which is what I thought I was doing, which you will see again later. So, because there's different ways of doing this, and I was in error which one I was doing. So, to correct, X is a pointer to a box. This box is a new node that has 100, and so we have this. We have X is a box that has 100, and what we want to do is add another box that has 200 to the end. Okay? Everybody with me? Yes? Yes, and that happens right here in the constructor. Every time we do one of these boxes, we automatically set it to null. Okay? But we have to write that into the class. The compiler doesn't do that. We just made our class do that, because otherwise our class would do random things and we would be unhappy. Okay, so I made a mistake. Who's still with me? Who thinks they're with me? Who's against me? Okay, just checking. All right, so now what we're going to do is we want to set this pointer right here to be pointing at a new box. And the way we have to do that is we have to follow this pointer and find the box that has 100. And then set the value here to be this newly created node. Everybody kind of with me on that? So, since we're starting here, we have to reel up the string until we find the first Coke bottle, and then we can do things with it. So we dereference the pointer. When we get there, we use the set next node call to be a new node that's created. So, how do we dereference the pointer? Star X. So this dereferences the pointer, and we have to put parentheses around it, I believe. Let me just compile this really fast to make sure I'm not screwing up worst. So we put parentheses around it. This says, follow the pointer to X. Follow the pointer that's stored in X. And when you get there, call the set next node on it. So the star X says, follow this pointer to X. When we get there, call the set next node method, which is right here, and give it a brand new node that has a value of 200 in it. All right, does that make sense? Who's with me conceptually? Okay. Question? Yeah, absolutely. So this first line right here, node star X, says we have a box that's an address of a node, and we point this to point at a brand new node that doesn't have a name but has a value of 100. So we have this box, which is up here. It's named next X. This is our node star X right here. That's it. And we has a pointer that has a box that points at 100. So that's what this first line does. Good with that? The next line says, okay, we have to break this down. What's the first thing that gets done? Parentheses. So what's inside this parentheses? Star X. And what does star X mean? It's dereference, which means just go to the thing that's the end of the pointer. So the first step that happens is the star X that goes to the thing that's the end of the pointer. Now we are working with this box right here, this node. And then we say, for this node, call the set next node value. What set next node value does is changes the value of the pointer that's in here. And then what happens is what we're setting it to is a new node that has a value of 200. So the new node 200 creates this new box. it has an address, and then we store the address right in here. All right, does that make sense? Everybody good? Yes? We did. And the new call returns a pointer value. And so we say set next node, this whole thing in here has to be a pointer value, and it is a pointer value because that's what new gives us. That's just how new works. It returns a pointer value. Yeah? Where is, say again? Yeah, let's look at that. Here's set next node right here. Here's the, yeah, and new node comes from this parameter right here, right? And this parameter up there is actually what's up here, right down here. So we create, this thing says, okay, we have to set next node, but we have to do what's in the parentheses first. So what we do is we create a new node, 200. This node has no name, but it does have an address, and that address is what gets put into set next node, and that's what gets stored in there. Okay. Everybody good? All right, I have a very special piece of candy, a peanut butter cup, which I normally never throw out in class. I eat them all myself. For the person who can tell me how to print out the value of 200 here. Go ahead, sir. So one of the guesses is C out asterisk asterisk X. Anybody think that'll be right? Sorry. Next contestant. Yes.
So you do the dereference.
Uh-huh. Yeah.
And then you have a bat-shaped thing, and then an equals because it's an overload operator.
Sorry, a bat-shaped thing like this?
Yeah, but only one of them. And then an equals, and then a print, but we need like a class.
Okay. This isn't going to work either. Yeah. Sorry. Dot get next node. Uh-huh. Like that. All right, let's give this a shot and see. It compiles, and we will run it, and we're going to get an address instead of 200. Whoops. So we got the address. So here's what you suggested, which is dereference X, and when we get there, call get next node, which will tell us the address of this thing. Okay. How many of y'all think this is turning into something quite horrible? I do too. And you know what? The people who wrote C++ also thought this was horrible. Let's step it down. I've got a butterfinger here for whoever can print out just the value in 100. Who can do just 100? Nope. I could. Okay. So here's the deal. If we want to print out just what's in X, all we have to do is get dereference X and say get data. I should have done this one first. Okay. So what this says is dereference the pointer in X. When you get there, call get data and print out what it returns. So we start at X, we dereference it, we end up at this box, we call get data. What comes out? 100. Okay. This notation is absolutely horrible. Like having to put the parentheses to get the dereferencing in there is horrible. Absolutely horrible. So because it's so horrible, we have an easier way of doing it. Is that what you were trying to say? The bat-shaped thing? It's okay. I actually like that. I'm going to start. It's the arrow, but all right. These two things are equivalent. X arrow get data is the same thing as parentheses star X dot get data. This means dereference the pointer, and when you get there, call get data. This means starting at X, go to this thing and call get data. They are the same. So when we run this, we should see 100 print out twice, because we printed it out two different ways. Pardon? They're both right here. See out. I printed the one out by dereferencing, and I printed one out by using the arrow operator. Oh my God, the second one's so much better. The second one is so much better. And I realized while I was trying to get you all to print out the 200 that it was going to take like 10 minutes just to figure out how to print out the other one using this notation, because there's like a maze of parentheses that have to be in the right order and stuff. So, all right. Given that we have the arrow operator, who wants to take a shot at printing out the 200? It's easier. Yes. Yeah, then what? Yep. So now we printed out the 200. So here's what we had to do. We started at X. We said, hey, follow X. When you get there, call get next node. So we started at X. We got there. We said get next node. We did. And then we called the arrow on that and said, hey, go there. I like that noise. And when we get there, do get data. And then it printed out the data. How does that sound? How about if we add like a few more things on here? How would you like to do that? Who wants to tell me how to add one more node onto the end of this with the value of, say, 1,000? What? Come on, nobody's got the peanut butter cup. I'm needing it myself. Talk me through it. If we did parentheses star x set next node again, we would be overwriting the value that we had in there. We would have a memory leak. Yeah. Go ahead. And what are we setting it to? What? Y'all think that's correct? Now, when we run it, we won't see the output, so how do we print it? And by the way, that is correct. You're the awardee of the first memorial peanut butter cup. How do we print this out? I have another peanut butter cup up here. Who wants to print it out? I think, if I didn't need them all. Go ahead. All right, how many of y'all think that's going to work? Yes? Yay, that works as well. All right, so here's the deal. In practice, we are never going to do it this way because it's cumbersome, right? Isn't it cumbersome? Yeah, but I want you to understand, I want you to be able to, I really want you to be able to draw pictures like this, like I drew right there. And the reason I want you to be able to draw pictures like that is because if you can draw the pictures, you can understand what's going on. Does that make sense? Now, I have one more handout, and essentially it's like another version of what we did right here. It's got the node class on the front and some stuff on back. And I would like you for next class to take a moment when you're looking at the videos and just draw out what's on there. So, all right. I'm going to give you a lot more video viewing because since I messed up the other one, we're a little bit behind. But it's all about this type of stuff and how to do it. Any questions before we go away for the weekend? Yes, I'm actually going to try and get the code review working this time. So if nothing else, just for my own peace of mind. So I'll post that today too. It's pretty easy. It's just a chance for you to look at how other people solve stuff. So anybody not get some of these yet? One sec. All right. Any last questions? I mean, we're a minute or two early, but there's not much I can do in that minute or two today. What? Yep, there's plenty more extras. Anybody not get one? Here you go. You can keep. All right, have a very good weekend.